Welcome to Understand the Math. In this Calculus 1 video, we're learning how to solve related rates problems where two or more quantities change with respect to time. We'll start by going over 4 steps that you can follow to solve these problems and review some of the standard formulas you'll need to know. Then we'll work through 8 classic examples, including problems with circles, spheres, cones, ladders, shadows, angles of elevation, moving cars, and a boat being pulled to a dock. Be sure to download the free guided notes to follow along and work through these examples with me. Let's start by going over the steps that you can follow to solve any related rates problem. Related rates are just problems where two or more quantities connected by an equation are changing with respect to time. By differentiating the equation with respect to time, the known rate of change of one quantity is going to be used to find the unknown rate of change of another quantity. After teaching related rates problems to students for many years, I've come up with 4 steps that you can follow to more easily solve these problems. The first step is to read the problem carefully. And then the second step is to organize the information into 4 categories. We'll go over these when we go over the examples, and then assign variables. The third step is to differentiate the equation with respect to time and solve for the unknown quantity. And then number 4 is just a reminder that you always need to include units in your final answer. Down below, I have listed 6 formulas that you will often need to know when you're solving related rates problems. The first one is the area of a triangle. The second is the area and circumference of a circle. The third is the volume and surface area of a sphere. Number 4 is a little bit tricky. It is similar triangles, and it involves the ratio of the side lengths of a triangle. The ratio of the smaller side lengths, A divided by B, is equal to the ratio of the larger side lengths, capital A divided by capital B. Number 5 is the volume of a cone, and then number 6 is the volume of a cylinder. If you download the free guided notes, you will have these formulas to use when you solve related rates problems. We are now going to go over 8 classic related rates problems. You'll see at least some of these when you study related rates. We're going to look at a related rates problem that involves a circular oil spill. We're told that oil spills from a ruptured tanker and spreads in a circular pattern. The radius of the spill increases at a constant rate of 1 meter per second. We want to find how fast is the area of the spill increasing when the radius is 30 meters. Now that we've read the problem carefully, we want to go ahead and fill in these 4 categories that I've listed here with the information from our problem. Since the oil spreads in a circular pattern, I went ahead and I put a circle down here for our diagram. We need to assign a variable to this. So if we talk about the oil spreading, we are going to be looking at how the radius changes. So let's go ahead and we'll put an R down there for radius. Now let's look at what we're given. We are told that the radius of the spill increases, so that is dr dt. At a constant rate of 1 meter per second, so we're going to set dr dt equal to 1 meter per second. Make sure to include units when you're putting down this information. We want to then find how fast is the area of the spill increasing, so that's dA dt. And there's always a when. The radius is equal to 30 meters. So we'll put a line here and say that is when R is equal to 30 meters. And now we have to find an equation. We want to find an equation that relates what we're given, such as the rate of change of the radius, to what we want to find, the rate of change of the area. So we need to think what formula that involves a circle has area and radius in it. And that formula is A is equal to pi r squared. Now what we need to do is we need to differentiate this equation with respect to time. Let's go ahead and we'll write down our equation. We have A is equal to pi r squared. And then we're going to take the derivative with respect to time of both sides. So we have dA dt is 2 pi r times dr dt. Both of these quantities are functions of time. Now we want to let our radius be equal to 30 meters. So we're going to find dA dt when r is 30 meters. So this is 2 pi times 30 meters times dr dt, which we are given, and we are told that that is 1 meter per second. So this gives us an answer of 60 pi meters squared per second. We can now say that the area of the spill is increasing at a rate of 60 pi meters squared per second. We are now going to look at a related rates problem that involves a spherical balloon inflating. We are told that the radius of a spherical balloon is increasing at a rate of 4 millimeters per second. We want to find how fast is the volume of the balloon increasing when the diameter is 80 millimeters. Since this problem involves a spherical balloon inflating, I went ahead and drew a diagram of a sphere. Now we just have to put some variables in it. Let's start by putting down the radius, and we'll call that r. And now let's see what we're given. We are told that the radius is increasing, so that is dr dt, at a rate of 4 millimeters per second. So we'll set this equal to 4 millimeters per second. Make sure to put the units down. We want to find how fast is the volume increasing. So we're going to find dV dt when the diameter is 80 millimeters. Now we need to find the equation. We need to find an equation that relates radius to volume of a sphere. And that equation is the volume is 4/3 pi r cubed. Before we go ahead and differentiate our equation, we need to add one more piece of information. We want to find dV dt when our diameter is 80 millimeters, but our equation is in terms of radius instead of diameter. So let's just put down this is the same as when the radius is 40 millimeters. And we'll use the radius instead of the diameter. Let's start by writing down our equation. V is equal to 4/3 pi r cubed. Now we're going to take the derivative with respect to time of both sides. So we have dV dt is equal to 4/3 pi times 3r squared times dr dt. So this is just 4 pi r squared times dr dt. Now we want to find the rate of change of the volume when our radius is 40 millimeters. So we're going to have 4 times pi, and now r is 40 millimeters, and that's squared. And then our dr dt was given to us, and that was 4 millimeters per second. We have a lot of 4's in here. When you go ahead and you multiply this out, we end up with 25,600 pi millimeters cubed per second. It's really common to put an answer in terms of pi because we don't have an exact number for pi. So when we put pi in the answer, that is an exact answer. If we were to plug in pi as 3.14, we would only get an approximate answer. We can now say that the volume of the balloon is increasing at a rate of 25,600 pi millimeters cubed per second. We're going to go over a related rates problem that involves the filling of a conical tank. We are told that water is being pumped into an inverted conical tank. I have that picture down here in the diagram so you can see what it looks like. And the water is being pumped in at a rate of 2 meters cubed per minute. We're told that the tank has a height of 6 meters and a base radius of 4 meters. We want to find out how fast is the water level rising when the water is 2 meters deep. Let's now write down what we're given in this problem. We are told that the water is being pumped into the tank at a rate of 2 meters cubed per minute. So that means the rate of change of the volume is equal to 2 meters cubed per minute. And that's positive because water is being pumped in. We're told that the tank has a height of 6 meters. So we'll say h is 6 meters. And then a base radius of 4 meters. So r is 4 meters. And let's put that the radius is 4 meters. And then the height of the tank is 6 meters. Now let's look at what we have to find. We want to find how fast is the water level rising. So when the water is rising, the height of the water is changing. So we want to find dh dt when we're told the water is 2 meters deep. So that means the height is 2 meters. Now we need to think about an equation. We need to find an equation that is going to relate the volume of our conical tank to our height. That formula is the volume is 1/3 pi r²h. Let's now look at this equation that we just wrote down. Our equation has a volume in it. It has a radius and it has a height. We want to find dh dt. We are given dv dt, but we are not given any information about dr dt. So what we have to do is we have to put r in terms of h. And the only way that we know how to do that is to use similar triangles. So I am going to take just the cross section here of our cone. We were given that the radius is 4 and the height is 6. Now let's think about some water being pumped in. Let's say that this is how much water we have. So we can call this the radius and then this part here the height. We have then two similar triangles. Here's the first one, where we have radius 4, height 6. And then our second one, we have a radius and a height. And they share common angles, so we can use what's called similar triangles. Similar triangles tell us that the ratio of the size of the conical tank, 4/6, is equal to the ratio of the radius to the height. We can then solve for r, so we find that r is equal to 4/6 times h, which is 2/3 times h. Let me go ahead and highlight that because that's what we're going to plug into our formula. Our formula is v is equal to 1/3 pi r²h. Now we're going to substitute in that r is 2/3 h. So we have 1/3 pi, 2/3 h. That gets squared times h. Our volume then is 2 squared, which is 4. And then we have 3 times 3 times 3, which is 27. So we have a 4/27 pi h cubed. Now we can take the derivative. We have dv dt on the left, and on the right, we have 4/27 pi times 3h squared times dh dt. Let's go ahead and cancel that 3 out. This then is 4/9 pi h squared dh dt. Now let's think about what we want to find. Let's go back up here. We want to find dh dt. So I am going to go ahead and highlight dh dt. That's what we want to solve for. So we can say that dh dt is going to be 9 times dv dt, all divided by 4 pi h squared. We want to find the rate of change of the height when our height is 2 meters. So this is 9, and then dv dt, let's go back up. It is 2 meters cubed per minute. 2 meters cubed per minute. And we divide that by 4 times pi times 2 meters squared. It's really important to put units in at this point so that you know what the units for your final answer are going to be. 9 times 2 is 18. And then in our denominator, we have 2 squared, which is 4, times 4, which is 16. So we have a 16 pi. And then our units are going to be meters per minute. We can divide both the numerator and the denominator by 2. So this is 9/8 pi meters per minute. This tells us that our water level is rising at a rate of 9/8 pi meters per minute. We're now going to look at a related rates problem that involves a ladder sliding down a wall. We are told that a ladder 10 feet long rests against a vertical wall. The bottom of the ladder slides away from the wall at a rate of 2 feet per second. We want to find how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall. I went ahead and drew our diagram. This is our wall. This is our ladder. And then we'll just call this the ground. The bottom of the ladder is moving this way, and then the top of the ladder is moving down this way. Before we write down what we're given and what we want to find, we have to assign variables to our picture. I am going to let this distance be x, this distance be y, and then we're told that our ladder is 10 feet, so we'll make the hypotenuse equal to 10. Now let's see what we're given. We are told that the bottom of the ladder slides away from the wall, so that means dx is going to be changing with respect to time at a rate of 2 feet per second. And we want to find how fast is the top of the ladder sliding down the wall. That means that y is going to be changing with respect to time. And that's going to be when the bottom of the ladder is 6 feet from the wall. So that's when x is equal to 6 feet. And then now we have to find an equation. We need to find an equation that is going to relate x and y. We have a triangle, and this angle is 90 degrees, so we can say that x squared plus y squared is equal to 10 squared. We'll go ahead and put that this is x squared plus y squared is 100. Now we're going to go ahead and we'll take this equation and we are going to differentiate it with respect to time. We have d dt of x squared plus y squared is equal to the derivative with respect to time of 100. On the left, we have 2x times dx dt, and then we have 2y times dy dt, and that is equal to 0. We want to find dy dt, so let's go ahead and solve for that. Dy dt is going to be minus 2x dx dt, all divided by 2y. So this is minus x times dx dt, all divided by y. Let's go back up here to the top. We want to find dy dt when x is equal to 6 feet. So let's go ahead and put this down. We want dy dt when x is 6 feet. Now let's go ahead and let's look over here at our equation. We have an x in our equation, but we also have a y in our equation, and we don't know what y is. So we have to use our equation here that relates x and y to find what y is when x is 6 feet. So I'm just going to say we need to find y when x is 6 feet. So we have x squared plus y squared is 100. Let's plug in that x is 6. So we have a 6 squared plus y squared is 100. So this gives us y squared is 100 minus 36, which is 64, and that's really nice because the square root of 64 is just 8. Now we can go back up and say that when x is 6 feet, y is 8 feet. And we can go ahead and plug this in. So we have a minus x, so that's a minus 6 feet, times dx dt. We have to go back up. That is 2 feet per second. So we'll plug in 2 feet per second. And then we're going to divide this by y, which is 8 feet. This gives us a minus 12 over 8 feet per second. We can divide both of these by 4, so we end up with minus 3 over 2 feet per second. When you are solving related rates problem and you get a negative for an answer, what you need to do is go back up to the original problem and find out exactly what you're being asked to find. We want to find how fast is the top of the ladder sliding down the wall. The word down takes the place of the negative. So in our answer, we need to not write the negative and instead just say that the top of the ladder is sliding down at 3/2 or 1.5 feet per second. And I'll go ahead and highlight that answer. Let's now look at a related rates problem that involves the tip of a shadow moving. We are told that a street light is mounted at the top of a 15-foot tall pole. I put a diagram down here so that you can visualize what this looks like. We're told that a person 6 feet tall walks away from the pole along a straight path at a speed of 4 feet per second. We want to find how fast is the tip of the person's shadow moving when the person is 30 feet from the pole. What we're going to do first is look at our diagram and put some variables in there, and then we'll write down what we're given, what we need to find, and then the equation that relates those two. We're told that the street light is on top of a 15-foot pole, so we'll mark this length as 15. And then we have a person that is 6 feet tall, so we'll label this as 6, and they are walking away from the pole. So let's just make an arrow like this so we can see the direction that they're walking. And they walk away from the pole at a speed of 4 feet per second. So that means we need to set a distance here equal to x, because dx dt will be the speed that the person is walking. We want to then find how fast is the tip of the person's shadow moving. This right here is the tip of the shadow, and we want to see how fast that's moving, so we need to assign a distance to this, and I'm just going to label that L. So let's say here that x is the distance from the person to the pole, and then L is our distance from the shadow, or the tip of the shadow, to the pole. Now let's go ahead and let's put down what we are given. We are told that the person walks away from the pole at a speed of 4 feet per second. So we can now say that dx dt is equal to 4 feet per second. And we want to find how fast the tip of the person's shadow is moving. So that is going to be dl dt. And we want to find that when the person is 30 feet from the pole. So that is when x is 30 feet. Now what we need to do is we need to find an equation that relates x to L. We are going to use what's called similar triangles to get this relationship. I'm going to go ahead and copy down our big triangle. And let's go ahead and let's label this. We have this side is 15 and this distance is L. And now we're going to have a smaller triangle, and that's going to be the height of the person, and then this length right here. We're told that the person is 6 feet, so we can label that as 6. And then now we have to find this distance right here. So let's go back over here to our picture, and I want to highlight this distance right here. That distance is this distance, and that is going to be L minus x. So let's come down here and let's write down the equation for our similar triangles. We have the ratio of 15 is to L as 6 is to L minus x. Now what we're going to do is cross multiply. So we have 15 times L minus x is equal to 6L. So that is 15L minus 15x is equal to 6L. So if we keep the L's on the left, we're going to have 15 minus 6, so that is 9L, and we get a 15x on the right. And we want to find dl dt, so let's solve for L. So this gives us that L is 15 over 9x. And let's see, we can divide 3 into both of those, so we get 5 over 3x. Similar triangles are hard, but once you have it, the equation is actually pretty simple. So we end up with the equation L is equal to 5 over 3 times x. Let's go back up here and see what we want to find. We want to find dl dt. So we are going to take the derivative with respect to time. So we have dl dt is equal to 5/3 times dx dt. And we want to find dl dt. Looks like we have to go back up again when x is 30. So x is 30 feet. So this is 5/3. Going back up once more, dx dt is 4 feet per second. So this gives us an answer of 20/3 feet per second. So we can now say that the tip of the person's shadow is moving at a rate of 20 divided by 3 feet per second. Before we finish, I just want to point out one thing, which I think is kind of unique to this problem. Notice that we did not use x is equal to 30 feet. What that means is the rate of change of the tip of the person's shadow doesn't depend on how far the person is from the pole. That rate stays the same no matter where the person is located. We're going to be looking at a related rates problem that involves an angle of elevation. We are told that a rocket is launched vertically upward from the ground. I have a little picture drawn down here so that you can see what that looks like. And it is rising at a rate of 40 meters per second. There is an observer that is standing 60 meters away from the launch pad. We need to find at what rate is the angle of elevation from the observer to the rocket increasing when the rocket is 80 meters above the ground. What we're going to do now is we are going to put in some variables in our diagram, and then we're going to fill in what we're given, what we need to find, and then the equation that relates what we're given to what we want to find. I'm going to mark that this point here is our observer. We are assuming that the observer's eyes are at ground level, so the vertical distance to the rocket is just the height above the ground. If the observer's height were included, we'd adjust the vertical side of the triangle by adding that height. Let's let the distance from the rocket to the ground be equal to y. And then this is our angle of elevation, and we're going to let that be equal to theta. The other piece of information that we need to put in our diagram is that the observer is 60 meters away from the launch pad. Here's the launch pad. So we're going to put this distance is 60 meters. Now let's see what else we're given. We are told that the rocket is rising at a rate of 40 meters per second. So the rate of change of the rocket is dy dt, and that is equal to 40 meters per second. We want to find at what rate the angle of elevation is increasing, so that is d theta dt, when the rocket is 80 meters above the ground, so that is when y is equal to 80 meters. Now what we have to do is we have to find an equation that relates y and theta. So here's y and here's theta. And then we don't know anything about the hypotenuse, so we're also going to have to use this distance of 60 meters. The trig equation that's going to relate these three variables is going to be tangent of theta is equal to y over 60. Now what we're going to do is we're going to take that equation and we are going to differentiate it with respect to time. So let me go ahead and write our equation down here. Tangent theta is y over 60. And we're going to take the derivative with respect to time of both sides. So the ddt of tangent theta is d dt of y over 60. The derivative of tangent is secant squared theta times d theta dt, because it's a function of time. And then we have a 1 over 60 that we can pull out on the right-hand side, and then we have a dy dt. We want to find d theta dt. So let's go ahead and let's solve for that. We have d theta dt is equal to, let's put the dy dt up here on top, and then in our denominator we have 60 secant squared theta. To make this easier, let's use the fact that 1 over secant is equal to cosine. So we can write this as cosine squared theta times dy dt, all divided by 60. And I'm going to go ahead and put that our 60 is in terms of meters. Now we want to find d theta dt when y is 80 meters. Notice in our equation that we have cosine squared theta. So I'm going to put down here that we have to find theta when y is 80 meters. I feel like this is the part that students always get confused with. Let's go ahead and let's draw our diagram again. We had a triangle. Here was our theta. This distance here was 60, and now we're told that this distance is 80. And we need to find cosine theta. So I'm going to let our hypotenuse be equal to z, and we can say that cosine theta is adjacent divided by hypotenuse, so that is 60 over z. And now we need to know what z is. I think this is why it's confusing, because you have to find so many things. Z is going to be the square root of 60 squared plus 80 squared. So let's see, this is the square root of 3,600 plus 6,400, which is the square root of 10,000. So that's at least nice. That is equal to 100. So we can say that cosine theta is 60 over 100, which is 6 over 10, and then dividing both by 2, we get 3 over 5. So let me go ahead and highlight this. Cosine theta is 3 over 5. Now we're going to take this and go ahead and plug it back in. Let me draw an arrow here so you can see where I am. We're going right up here. So cosine squared theta is going to be 3 over 5 quantity squared. We need dy dt. Let's go back up. That is 40 meters per second. And then we divide this by 60 meters. So we have 9 over 25 times 4 over 6. Now, here is something super important. We have to think about units. Because theta is an angle, the rate of change of our angle is going to have units of radians per second. Because the meters here canceled out. Now let's see, we can go ahead and simplify this. We have 36 divided by 6, which is just 6. So we get an answer of 6 divided by 25 radians per second. This tells us that the rate of change of elevation from the observer to the rocket is increasing at a rate of 6 over 25 radians per second. We're going to be looking at a related rates problem that involves two cars that are moving away from each other. We're told that two cars leave the same intersection at the same time. Down here in our diagram, this is our intersection. We're told that car A travels north at 45 miles per hour and car B travels east at 60 miles per hour. We want to find at what rate is the distance between the two cars increasing 2 hours later. The first thing we want to do is fill in some information into our diagram. Let's first think about car A. Car A is traveling north, so let's just label this car A. And then car B is traveling east, so we'll label this car B. And let's go ahead and let's put variables with this. Let's let car A be the variable y and car B be the variable x. Now let's write down the rates that we're given. We're told that car A travels at 45 miles per hour, so that means that dy dt is 45 miles per hour. And then car B is traveling east at 60 miles per hour. So that means dx dt is 60 miles per hour. We want to find the rate at which the distance between the two cars is increasing. So we need to go back to our diagram and we need to put a variable for that distance. And I'm going to call that variable z. So we want to find dz dt when 2 hours have passed. So this is when t is equal to 2 hours. Now what we need to do is we need to find an equation that relates x, y, and z. We can get it from the Pythagorean theorem because we have a right angle here. So that is x squared plus y squared is z squared. Now what we're going to do is we're going to take that equation and we're going to differentiate it with respect to time. So let's first write it down. We have x squared plus y squared is equal to z squared. Now we're going to take the derivative with respect to time of both sides, x squared plus y squared, and then we have d dt of z squared. This derivative is 2x times dx dt plus 2y times dy dt is equal to 2z times dz dt. Let's notice that our 2's are going to cancel. And let's go back here and see what we want to find. We want to find dz dt. So that's right here. So let's go ahead and let's solve for that. We can say that dz dt is equal to x dx dt plus y times dy dt, all divided by z. We want to find dz dt when t is equal to 2 hours. We are given what dx dt is, we're given what dy dt is, but we do not know what x, y, or z are equal to. But we can find those out because we know how fast they're traveling per hour, and they're going to be traveling for 2 hours. Let's come down here and let's figure this out. So when t is equal to 2, x is going to be 60 miles per hour times 2 hours. So that's going to be 120 miles. Y is 45 miles per hour times 2 hours. So that is 90 miles. And then z, we are not given a rate for. So what we're going to have to do is go back to our diagram. I'll go ahead and recopy it right here. This is x, this is y, and this is z. And x is 120, and y is 90. So z is going to be the square root of 90 squared plus 120 squared. I'm leaving off units just for a minute. So this is the square root of 8,100 plus 14,400. And then this is the square root of 22,500. And that actually is a nice number. That turns out to be 150. And then we'll go ahead and put miles for our unit. So we have X, Y, and now we have Z. And we can go back up to here and plug everything in. So this is X, which is 120 miles, times dx dt, which we're given up top, was 60 miles per hour, plus Y, which is 90 miles, times dy dt, which we were given as 45 miles per hour. I'm going to have to write really small here. And we're going to divide all of this by z, which we just found to be 150 miles. This is equal to 7,200 plus 4,050, all divided by 150, and we'll put units here in just a minute. This ends up being just 75. Now let's look at our units. Notice that our miles cancel out, so our units are just miles per hour, which is what we would expect. We can now say that the rate at which the distance between the two cars is increasing is 75 miles per hour. Let's now look at a related rates problem about pulling a boat with a winch. We're told that a boat is being pulled towards a dock by a rope attached to a winch, and that winch is 5 meters above the water level. The rope is being wound in at 2 meters per second, and we want to find how fast is the boat approaching the dock when 13 meters of the rope is out. I put a diagram down here, put a little boat. That's about as good as I could draw it. And now let's go ahead and let's label things. This right-hand side is our winch. And then this distance here is our rope. And then this point here is our dock. Our boat is heading towards the dock. Now what we need to do is assign variables to our diagram. We are told that the winch is 5 meters. So we're going to label this distance 5 meters. The distance from the boat to the dock is changing, so we're going to let that be variable x. And then the length of the rope is changing, so we are going to let that be the variable capital R. Now let's write down what we're given. We are told that the rope is being wound in at a rate of 2 meters per second. So we can say that dr dt is equal to minus 2 meters per second because the amount of rope is decreasing. We want to find how fast the boat is approaching the dock, so that is going to be dx dt. And we want to know that when 13 meters of the rope is out, so that is going to be when r is 13 meters. Now what we need to do is find an equation that is going to relate capital R and x and the length of our winch, which is 5. So we need to relate x, r, and 5. That equation comes from the Pythagorean theorem because we have a right angle here. So we have x squared plus 5 squared is equal to r squared. So we can write this as x squared plus 25 is r squared. We're now going to take that equation and we are going to differentiate it with respect to time. So let's write down x squared plus 25 is r squared. And we're going to take the derivative with respect to time of both sides of our equation. So this derivative is 2x times dx dt plus the derivative of our constant, which is 0. And then on the right-hand side, we have 2r times dr dt. We want to find dx dt, so we're going to solve for that. So we have dx dt is equal to 2r times dr dt, all divided by 2x. Our 2's cancel, and we end up with r times dr dt, all divided by x. We want to find dx dt when r is equal to 13 meters. Notice up here in our equation that we can substitute in that r is 13. We are given dr dt, however, we do not know what x is. So we are going to have to use our equation x squared plus 25 is equal to r squared to find what x is. Let's go ahead and let's do that down here. I'm going to write down that x squared plus 25 is equal to r squared. Let's substitute in that r is 13. So we have x squared plus 25 is 13 squared. And we know 13 squared is 169. So x squared is 169 minus 25, and that is 144. And so x is equal to 12. And we'll go ahead and put a unit there. It is in terms of meters. Now we can go ahead and go back up, and we can plug in everything up into that equation. Our r is 13 meters, and then dr dt we were given up here is minus 2 meters per second. And then we just found that x was equal to 12 meters. So this is minus 26 over 12 meters per second, and we can divide by 2 in both of those. So we get minus 13 over 6 meters per second. Whenever you solve a related rates problem and you get a negative, you need to go back up to the original problem and find out what you're being asked to find. We want to find how fast the boat is approaching the dock. So that means the distance from the boat to the dock is decreasing. And that's why we got a negative answer. And we can write our answer and we can say that the boat is approaching the dock at 13 over 6 meters per second. And let's go ahead and highlight that answer. And that's it. You've learned how to solve related rates problems step by step, from organizing the information to differentiating with respect to time and then solving for the unknown rate. To really master related rates, make sure you work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.